Okay.
Okay, good day. So today we will be presenting our assignment, which is for fluid mechanics assignment piping system. As you can see in this slide, this is our group members. First, we have MOHAMAD, AMIRUL, HAKIMI. Second, we have PRAVINRAJ. Then we have ELVYN, and then KISSHOCK, KUMAR, and NAVENDRAN. Okay, first of all, I will start with the assignment introduction. Piping system and pump operate together to carry fluids in a range of commercial, industrial, and domestic applications. The piping system's function is to move gases or liquids from one location to another. It consists of a system of interconnected fittings, valves, pipes, and other components. Pumps are crucial parts of the system because they provide the energy required to overcome the resistance and send the fluid through the pipes. Okay, the next one is for the theory and the concept of piping design and pump selection. So designing fluid transport system involves two key components, which is piping design and pump selection. Piping design requires choosing appropriate materials and pipe sizes based on fluid characteristics, temperature, pressure, and flow rates, while ensuring compliance with industry standards and accounting for thermal expansions and maintenance needs. Pump selection involves choosing the right pump and specification based on hydraulic principles, performance curve, head, flow rate, and power requirements. The pump should operate near its best efficiency point for optimal performance. And also, efficient system performance depends on the integration of piping and pump design, requiring collaboration between experts to meet process requirements, regulatory standards, and safety considerations. And the next one will be presented by the next member.
So, okay. Good evening. My name is ELVYN. My metric ID is B092221 and 0068. So today I'll be talking about calculation, which is called pipe pump size and pump calculation. So first of all, our task given is our flow rate is 5 meter cube per millimeter, and our velocity in pipe is 3 meter per second, and the temperature is 130 degrees Celsius. So another thing, the total length of our pipe is 76 meter, and another thing from the chart of our water viscosity, then what we calculate our temperature chart is first temperature is 160 degrees Celsius and the mu one is 0.1736 meter Pascal per second. And second thing, second temperature is 30 degrees Celsius and then mu two, which is viscosity equal to 0.7972 meter Pascal per second. And then we calculate total viscosity, which is we get 0.6243 times 10 power negative 3 Pascal per second. And then we calculate a heat loss. The heat loss is 0.0833 meter cubic per second. And then we use the formula to find the diameter. So, so from through formula, we get the diameter which is called 9.64 millimeter. And then we did the calculation, the water power plus frictional resistance outcome so that we can find out the major loss during traveling in pipe. And then we did the total calculation, which is called how to find out pressure, which is rho times gravity times heat loss, and then times major loss, then divided by uh, which is called 0.7, and then we get 40.9 kilowatts. And then we did specification and pipe size selection, and we did some simulation. So from our this is our main simulation, and for this we get two main components for the cooling system that we mainly focus is and the pipe and pump and pipe specification. And then our pump specification is firstly we use centrifugal pump, which is an suction type. It has the size of 4 by 3, 10, an area of 70. The speed that is running is 2950 RPM and have the impeller diameter of 209.550 millimeters. The detailed specification of the pump is shown the diagram, and this is the diagram so far. So we choose this because it has a good operating notes, which is called region 70 percentage till 130 percentage, and has a good flow range. And this is one of the perfect pump for the for our project. So next will be presented by next presenter.
Okay, my name is Navendran and I'm going to present about the pipe size. The pipe size, the pipe for the system that we use is steel pipe. It has a diameter of 12.95 millimeter and roughness of 0.0046. We use 11 pipe with a relative same data and specification. The table below shows the details of each pipe that we use in done simulation. So the data below shows the 11 pipe of the data and the including with pipe names, node, inner diameter, length, mass flow, volume flow, velocity, total loss bar, entry pressure, and exit pressure bar. Next slide.
And next slide, go.
Factors that affect centrifugal pump output and efficiency. The pump design and quality. High efficiency will meet contemporary pump with minimal internal clearance and optimal casing and inflows. Low efficiency, larger clearance or kinetic impeller design in older or poorly constructed pumps. Operating point, operating the high efficiency, operating the pump at its best efficiency point. Low efficiency, operating too far from the BAP, too high or low flow rates. Piping configuration, optimal pipe layout. Short, straight, and of the right diameter reduce friction losses. Bad layout, friction loss are increased by long twists or undersized pipes which lower efficiency. Pump output, impeller speed, RPM, increase impeller speed boosts the pump's head pressure and flow rate. The decrease is the head and flow rate are decreased with a lower impeller speed. Next is flow rate. So the increased flow rates have the potential to push the pump above its ideal operating point and result in higher energy consumption. And the decrease is, although they might not meet system requirements, lower flow rates can result. So next slide. Suggestion to improve the design of the project. Pipe sizing to maintain a velocity of less than 3 milliseconds. Use a pipe with an internal diameter of at least 188.1 millimeter. Pump specification. Choose a centrifugal pump with 31.7 meter of total dynamic head and a 300 millicube per hour capacity. Pipe material. Galvanized steel which provide better corrosion resistance and cost effectiveness compared to stainless steel. The next will be presented by Praveen.
Okay, thank you, Navendran. And my name is PRAVINRAJ, and my metric number is B0922100225. And today I'm going to present about the comparison between hand calculation and the simulation result. And for the hand calculation result, using the above data flow rate, which is 5 meter cubic per minute, and velocity, which is equals to 3 meter per square, 3 meter per second, and the formula for Q, which is AV. We can determine that diameter is 0.1881 meter or higher is the proper pipe diameter for the system. For the simulation result, the diameter of the pipe is 0.189 meter, which will be applied to the simulation, yielding the following results, which is velocity equals to 2.970 meter per second, and flow rate is equals to 0.0833 meter cubic per second. And the comparison between both of the result is we can determine that the flow rate and velocity values from simulation result match the given information. This indicates that the diameter value calculated is suitable for the piping system cooling process to avoid noise and erosion inside pipeline. Next. And for the discussion, the simulation results show that the values for power, head loss, pressure loss, and flow rate are lower than the theoretical calculations. This discrepancy arises due to the factors like topography, friction, and pipe fitting losses, not included in the calculations. The calculated power is 40.9 kilowatt, while the simulation shows only 19.98 kilowatt, indicating a significant power loss due to design simplifications and factors like inconsistent flow rates and temperature differences. The simulation head loss is 5.676 bar compared to the calculated, which is 0.324 bar, likely due to external temperature fluctuations and variations in pipe diameter and roughness. These factors highlight that the simulated piping system's efficiency at 72.66% of the calculated value is lower because real life conditions and complexities were not fully accounted for the calculations. And for the conclusion, all things considered, the cooling process pipe system is well designed and competent to fulfill the required performance standards. Still, there are several areas that need further focus. By lowering the piping system's flow rate will aid in lowering power usage, head loss, and pressure loss. Reducing the flow rate and utilizing a more efficient pump are more ways to lower pumps power usage. Another suggestion is to use larger or short pipes with fewer elbows, fittings, and also smoother pipe valve to minimize pressure loss and head loss in the piping system. All in all, a significantly more effective cooling process pipe system can be created by implementing these suggestions. And that's all from us today. Thank you.